welcome to another video of quantum field theory, and Happy New Year! So in my last video of quantum field theory, I believe it was quantum field theory 1E, we went over what's called Noether's theorem. Noether's theorem just says that symmetries imply what's called conservation laws. So a conservation law looks like this. It just says that the derivative of some conserved quantity, Q, conserved quantity, over time equals 0. So this statement is called a conservation law, and Q is what is called a conserved quantity. So Noether's theorem tells us that if we have some symmetry, there is some conserved quantity or some conservation law that goes along with that symmetry. And here is just some example that you guys might be interested in. It just says that, say, if we have x to x prime, and it leaves the Lagrangian unchanged, which means that the delta L is 0, we have a symmetry of the Lagrangian. And there is some motivation behind why we call it a symmetry. So, say we have some square, right? We have some red square. Now we can rotate the square by 90 degrees, and it looks the same, right? We changed the square. We technically just rotated it by 90 degrees, but it looks the same. Well, these aren't perfect squares. They're rectangles, right? But pretend that it is a perfect square. If we were to rotate it by 90 degrees, the square looks the same. However, if we were to rotate it by, say, 23 degrees, the square will look different. You can tell it apart from if it wasn't rotated. So this rotation of 90 degrees leaves the square unchanged, so we see that the square has a rotational symmetry about 90 degrees. That's what motivates us calling this a symmetry. So it isn't some like physical symmetry of the Lagrangian. The Lagrangian is a functional, right? But it just says that if the Lagrangian is unchanged by some transformation, it's a symmetry. Just like how the square, if it's unchanged over some rotation, we call it symmetrical. That's the motivation as to why we call it asymmetry. So, in the last video, we looked at Lagrangians that were symmetrical under space-time translations. So we considered a translation x, where x is some vector in space-time, or sorry, some point in space-time, really. And we changed it to x prime, where x prime just equals the original x plus another space-time point A. All right? And we found, and so we did some like math jargon, and we derived this continuity equation. By the way, if you guys are not familiar with this, check out my last video. That's a prereq for this video. So we derived this continuity equation in the last video, where this T mu nu here is what's called the stress energy tensor. So we found that if a space-time translation leaves the Lagrangian unchanged, it implies this continuity equation. All right? So we can, of course, expand this. By the way, this is actually an Einstein notation, so there is an implied sum over mu here, for mu to like whatever, how many parameters that we have. So partial mu, T mu nu equals 0. This is a summation over mu, by the way. So we can just expand this to get partial mu T partial naught T naught nu minus partial I T naught I. Minus partial I T naught mu equals 0. By the way, technically speaking, there's a minus here because our metric signature is negative along the diagonal, except for the first entry, the first time entry. So we have this equation over here. That's all we did is we just expanded our our continuity equation. So what do we do now? Well, what we can do now is we can just add both sides by partial I t naught nu, right? We can just add both sides by that. Oops, sorry, not equals. So we just add both sides, and we now get partial naught t naught nu equals partial I t naught nu. Oh, sorry, partial. This should be an. Wait, let me think. Yes, this should be an I. By the way, my bad. This should be an I, and it should be an I because if we were to expand this, it's just partial naught t naught nu minus partial 1 t1 nu minus partial 2 t1 nu minus partial 3 t3 nu. This should be a 2. And we just take this. Oops, sorry, these should be pluses. So we just take this and we just write it as ti, partial I ti nu. So we have partial naught t naught nu minus this. All right, that's where this comes from, by the way. So I has the indices from 1 to 3, and then we just have the zero indice, 0. So we have this over here, this relation. It just says that the derivative of the stress energy tensor, the zeroth component, right, or really the time derivative, since partial naught is just partial t, right? So the time derivative of the naught component of the stress energy tensor is just going to be equal to the spatial derivative. Okay. So now what we can do is we can look at the case where nu equals 0. We can look at cases where nu equals 1, 2, and 3, but for now let's look at the case where nu equals 0. So if nu is 0, this means that we have partial t naught equals partial 1 partial I t I naught. Okay? So the time derivative of the first component of the stress energy tensor equals the spatial derivative of the ti naught component. Sorry for the noise, by the way. I live in a house with siblings, so kind of unavoidable. So, well, what we can do now is we can just write this over here as the divergence of some vector j. This is just notation, because this is just the formula for divergence. If you guys might recognize it from vector calculus, right? To get the divergence of some vector field, we just take the derivative of like each component of that field. For example, the divergence of some field, let's just call it q. It's just partial q over partial x plus partial q over partial y plus partial q over partial z, right? And this should be the like the x component and the y component and the z component of the field, by the way. And we expand the field as qx, qy, and qz. That's where this is coming from. So it's not anything mysterious. That's what I'm trying to show. So we can write partial t naught is equal to some divergence of some vector field sorts of j. And let's just move that a bit closer. All right. So what we can do now is we can integrate both sides. Let's integrate both sides over some volume v with the three-dimensional volume element. So we're just integrating both sides. We're integrating both sides by some three-dimensional volume v. So that's this over here. Okay. So what do we do now? Well, what we can do is we can use what's called the divergence theorem. So the divergence theorem just states that we can just write this side. We can write the three-dimensional volume integral over some divergence of some vector field J as the integral of the infinitesimal volume element. This is called the divergence theorem. I'm just going to write that in red. The divergence theorem. You guys can look this theorem up in more detail for yourself. It's a very nice theorem in vector calc, used to make a lot of proofs. So this is just going to be integral d to the 3x of delta of, sorry, not delta, what is this symbol called again? Nabla? I forgot. But the divergence of J. Alright? And that's equal to this over here. Now we declare that our field vanishes. It vanishes as we approach infinity of this integral. We declare that it vanishes as we approach infinity. So that means that this entire integral is going to be 0. Since if our field vanishes as we approach infinity, this means that this integral will go to 0. So now we have this equals 0. So what have we just done here? Well, at first we had a continuity equation that told us the partial mu t mu nu equals 0. But remember, this isn't a conserved quantity. T mu nu is not a conserved quantity, or better said, this isn't a conservation law. It's better to say this. This is not a conservation law. That's what I mean. Because remember that a conservation law just says that dq over dt equals 0. This is not what this says. This is also not a conservation law. This law over here, partial t not nu minus partial I nu equals 0. This is also not a conservation law. Because it's not in this form, right? It's not a conservation law. What we've just done is we've just found a conservation law. This law over here is a conservation law. Oops, I made a slight, or I forgot to account for something. So technically speaking right now, we can just move this derivative to the front, and we get partial t integral over the volume t not equals 0. So all we've done is we just move this guy over. We are allowed to do that. We can just move the partial derivative over in front of the integral. And this is a conservation law. It is a conservation law. Let me just move these things down a bit to make up some space. So this over here is a let me just copy and paste it actually, because I'm gonna copy and paste it down here. This is a conservation law because we have that the derivative, time derivative, or partial over partial t really, of this entire thing is 0. And that's the same format as this over here. The derivative of some quantity j, some quantity q equals 0, then this is a conservation law. That's what we have here. Instead our q in this case, our conserved quantity, is going to be this over here. This is our conserved quantity. All right. So one more thing before we close off. Note that this is the conserved quantity for when we declared nu to be equal to 0. So we derive this for nu equals 0, right? Now remember that when we first started out, we started out with space-time translation, general space-time translation. So some point in space-time x was transformed into x plus a, some a vector. This is just some point in space-time. So that's going to be t then like x1, x2, x3, which would eventually be x, y, and z, right? Now, if nu equals 0, this means that, like, how do I word this? Let's go back to the front over here. Okay, so for nu equals 0, that's just the time component, right? Because again, we have x, we have t, x, y, and z for this space-time point. And for nu equals 0, that's our first component. This is nu equals 0. We can actually write this x as, I don't like this notation, but we can sort of write some space-time point as x nu, where we have values for nu. Here would be nu equals 0. Here's nu equals 1. Here's nu equals 2. Here's nu equals to 3. So for nu equals 0, this means that we are considering transformations of the time component, since time is the 0th component. Well, because time is the 0th component of some space-time event, some event in space-time. So it's the 0th component. Well, I'm repeating myself a lot, but for nu equals 0, that's just the time component. That's what I'm trying to convey here in a horrible way. So nu equals 0, that's the time component. So we just considered transformations for not x to x plus a. Well, it is x to x plus a, but more specifically, t to t plus a, or a naught, or sorry, a naught. Here. So we were considering, by setting nu to be 0, translations in time, specifically. Not transformations in x, y, z, t, but transformations in t. So under time translations of the Lagrangian, by setting nu equals 0, we are only considering time translations of the Lagrangian. And this is the conserved quantity for time translations, okay? Let's just write that down again. So for time translations, we get this quantity. And there's a special name for quantities there's a special name for conserved quantities of the Lagrangian under time translations. It's called the Hamiltonian. The Hamiltonian is defined as the conserved quantity under time translational symmetry of the Lagrangian. So the Hamiltonian tends to be the energy of a system. In classical mechanics, where we have the Lagrangian L plus T minus V, the Hamiltonian is just the total energy of our system. Here it's not. Here our Hamiltonian is this guy, right? And this is not the energy of our system. So the Hamiltonian is not always the energy. However, we will see in the short future that if we were to act on our Hamiltonian, if we were to have some vector, let's just call it, I don't know, psi, if our Hamiltonian acts on the vector, it will actually give out the energy of the system times the vector. So this is where the energy plays in. So we can say that the energy is the eigenvalue of the quantity that is conserved under a time translational symmetry of the Lagrangian. But the actual conserved quantity is the Hamiltonian, which will not be the energy in our case of quantum field theory. So that's the conserved quantity in time. Similarly, we can actually derive the conserved quantity in space. So what would that be? Well, remember, we considered nu to be 0. So let's just erase all this stuff here. Erase all of this. So, more things to erase. Okay. So we considered nu to be equal. Actually, where does it start? Yeah, this starts over here. Let's pretend that. I'm doing this quickly. Okay, so here we considered nu to be 0, right? We did, okay, nu is 0. We derived this, and from there we found out the conserved quantity for nu equals 0, which is time. Well, sorry, we found the conserved quantity for nu equals 0, which is the Hamiltonian, and nu equals 0 is just the time component of the space-time event. Instead of nu equals 0, we can consider the conserved quantity for nu equals 1, 2, and 3. And we do that in a very similar fashion. So we have partial naught t naught 1 plus partial naught t naught, sorry, yeah, okay, sorry, we don't do that. So yeah, so we just have this over here, and again, we're letting nu be only 1, 2, and 3 respectively. So we just do the same thing, but we just leave nu as being nu. We don't let nu be 1, 2, or 3, but nu can take on values of 1, 2, 3, but we don't write that explicitly. So let's do that. So we just take the, so what we do here is we just take the integral of both sides again over the 3 volume element. So it's just t naught nu, and that's going to be equal to the integral of partial I ti nu, right? And then again, we just let this be the divergence of some vector field. So now we have this over here. Okay. And then what we have to do is we just use the divergence theorem to state that this is just equal to the infinitesimal volume element v of the divergence. We're missing this over here. Let's just add that. Oh, by the way, technically speaking, this shouldn't be 3. This should be 2. By the divergence theorem, this should be a 2 when we apply the divergence theorem, not 3. My bad. Well, here it should be a 3, but when we use the theorem, it reduces down to a 2. So we have this. All right, and also, oops, I forgot to. Oh, what am I doing right here? I forgot to include the partial naught term. My bad. Remember, there's a partial naught term, so we have to include that as well. Partial naught t naught nu, and we have that. Yes, just forgot to include the partial naught term. So let's just include that right now. Partial naught, which is just the time component, really. So now we can just, so now we can just write that again, but use partial t since t is the 0th component. Now we have this over here. We say that it has to vanish, right, as it goes to infinity. Just the same thing as last time. And now we can move this partial t to the front. And now we have that. So you move it to the front. Oops, actually, let me double check my work. Yeah, it's good. So let's erase this over here. This is annoying. And here we have this. So this is the conserved quantity. So we have partial t q equals 0, where q is just the volume element, three-dimensional volume element of t naught nu. All right. And since nu can take on values for 1, 2, 3, and not 0, we're being a bit sloppy in our notation by saying nu. Really, we mean I. Since nu takes on values only 1, 2, 3, we relabel nu to being I, to make it clear that we are only considering values 1, 2, 3, and not the 0th value. The 0th value is for time, but 1, 2, 3 is for space, right? Since again, some point in space-time is t, x naught, x1, x2, where this is just x, y, and z. These are our spatial components. We have one time components. All right. So we call Q. Get ready for this. We call Q the What do we call it? We call it the conserved quantity. Conserved quantity for spatial translations, right? Since again we had x, some point in space-time x, turning into x plus a, right? We considered nu to be I, which is just 1, 2, 3, right? So we are only considering those spatial translations now. We're considering only x, y, and z turning into x plus a a1, yeah, and then y plus a2, z plus a3. So spatial translations give us some conserved quantity, q, and we call q the momentum operator. And that's what we define it as. And we call that p. So let's just relabel this to p. And it turns out, you probably guessed it, that when p acts on some state, it gives us the momentum of the system. So that's the relation to momentum. And in classical mechanics, it's actually the same thing. Space translations give us momentum as the conserved quantity. In QFT, it's not momentum anymore, it's the momentum operator. And this is how it's related to the classical momentum. All right. So yeah, that's the end of the Noether's theorem mini playlist. There are other symmetries that we can consider. In this video, we considered space-time symmetries. Just moving. It just really corresponds to just moving our coordinate system by shifting it in time or shifting it in space. That's what we considered. Well, we can also consider what are called internal symmetries, and that's where QFT shows its like glory. By internal symmetries, we can have conserved quantities that are more interesting. And it turns out that charge, for example, electrical charge is a conserved quantity for some particular symmetries for some particular internal symmetries. So external symmetries, we consider changing our space-time point to called external symmetries, or external transformations. And then internal symmetries, we have the field itself is changing, but the space-time points are dormant. Here we had that the field changes by consequence, right? Since it's a function of those space-time points, but we didn't have the field itself change without the points changing. For that case, we have internal symmetries. So you have phi, our field phi turns into, say, phi plus phi, what should I call it? Let me just call it phi. Well, let's just call it phi plus some amount, or just phi to phi prime. This is an internal transformation, and it gives us internal symmetries. That's a different case. We will cover this case like in the far future, that's outside the scope of this video, but there are internal symmetries, and we will study those in detail when we get to the standard model. One example of an internal symmetry is a U1 symmetry. This is the one that actually leads to the concentration of electric charge. That's the symmetry. And I did make a video on U1, by the way, so watch that one if you want to. And yeah, that concludes our video. Next video we will cover. I'll actually show you guys the particular Hamiltonian and the particular momentum operator in for a free scalar field in quantum field theory, and we will use those to do second quantization and stuff like that. Really cool stuff. See you guys in another video. I'm exhausted. Bye.